the last class we have started with binary numbers. So binary numbers is represented by 0 and 1. That means there are two integers to represent the binary numbers. Today we are going to discuss about the binary numbers. What is the largest number present in each of the binary number corresponding to the bits available. Then how to convert binary numbers to decimal numbers. So that is what we are going to discuss right now. So you can see here the decimal numbers and the corresponding binary number. Suppose you have only one bit. You are representing binary numbers in certain positions. Suppose in that memory location there is only one bit. We have given the concept of bit in the previous class. So one bit means it can either be 0 or 1, isn't it? Yes, 0 or 1 is the value. So the maximum value for that will be 1. 1 bit space is there, 0 or 1 are the two values, the maximum value is 1. It is binary, means the base is 2 and 1 bit is there. So 2 raised to 1 minus 1 is the maximum value corresponding to a 1 bit arrangement in which you can accommodate the maximum number. Next, to represent 2 we need 2 bits. So the first one goes to 0, the second one is 1. This is our number 2. Number 3. So this becomes 0 becomes 1 and this is 1 itself. So this is the maximum value that can be represented in a 2-bit space. Okay. If there are 2 bits, the maximum value you can represent is the value is 3. So 2 raised to how many bits? 2 bits. So 2 raised to 2 minus 1. So what is that? 2 raised to 2 minus 1 is 3. So the maximum value that can be represented in a 2-bit arrangement is 3. Now let us go to the next number. Next number, this will become 0, this will become 0. You will go to the next position. So this is a 3-bit representation. We need 3 bits to represent number 4. Next, number 5. This goes to 1, this is 0. Again, going to 6, this becomes 0. You go to the next position as 1 and so on. Now, this makes the maximum value for a 3-bit arrangement. 1, 1, 1. Beyond that you cannot go. So next number you have to go means you have to take a 4-bit. So this is a 3-bit digit. In this 3-bit, what is the maximum value? 7. How will you get it? It is a 3-bit. So n is equal to 3. So 2 raised to n minus 1 becomes 2 raised to 3 minus 1. That is how much? 8 minus 1 is 7. So the maximum value that can be represented by a 3-digit number is 7. Now going to the 4-bit. 4-bit minimum values, all the rest 0. The maximum position is 1. Then 9. This first position you give value 1. The others are same. This is 9, 10 and so on. So if you are representing, what will be the maximum value for this one? A 4-bit arrangement, 2 raised to 4 minus 1. So like that you can go up to any number of bits. Suppose there are n bits in your location. So the maximum value that can be represented in that n bit is 2 raised to n minus 1. So that is the largest number possible in an n-bit arrangement. So you have got some idea about the binary and decimal numbers. Now let us see how to convert a binary number to a decimal number. Let us take the simplest of the case. What is this number? It is number 2. You can see here it is number 2. Just like our decimal system itself, you can look at the value of the position, weightage. This has got base is 2. So this has got 2 raised to 0 position. This is 2 raised to 1 position. That is what I have written here. The same thing I have written down once more. This 0 has got position. Its weightage is 2 raised to 0. This has got weightage 2 raised to 1. So this has value 1 into 2 raised to 1 plus 0 into 2 raised to 0. That is 2 plus 0, which is equal to 2 itself. One more method is there to convert this binary to decimal. That is called double-double method. In the double-double method, what you do is, this is that whatever number you have, you take the leftmost digit, multiply by 2. 1 into 2. To that you add on the next digit. So that is 1 into 2 plus 0. That is 2 plus 0, value 2. The same you get here. Two different methods. Now let us take the next example. 1, 1, 1. Again, this one has got position 2 raised to 0, 2 raised to 1, 2 raised to 2. So you can see it here. 4 plus 2 plus 1 into 2 raised to 0 is 1. So this becomes value is 7. Now let us see the double method. Here again the same position. You take the leftmost digit, multiply it by 2, add the next digit to it, the whole thing multiplied by 2, again add the next digit, and so on. So you look here, this is 2 plus 1. This is 1 into 2, that is 2 plus 1. I have written down here into 2. The last digit you keep it like that. So this is 6 plus 1, 7. The same thing you get here. Clear? One more you can try. 1, 1, 1, 0. To get the position, this is 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3. So this is a weighted value. So multiply the corresponding digits by its weight. You get 1 into 2 raised to 3, 1 into 2 raised to 2, 1 into 2 raised to 1, plus 0 into 2 raised to 0. That is 8 plus 4 plus 2, which is equal to 14. The same thing you can try with the double method. So the first last leftmost digit you take, multiply it by 2, plus the next digit, the whole multiplied by 2, plus the next digit, the whole multiplied by 2, plus the last digit. So you simplify that, you get it as 70. So this is the conversion of binary to decimal. You can try any number of examples. Now let us see how to convert decimal numbers to binary numbers. This is also double method. We are taking number 5. Example. So you can divide with respect to 2. 2 is our base. So it goes 2 2s are 4. 2 times it will go. The remainder will be 1. I am writing the remainder here. Again I am going to divide by 2. It will go 1 time with remainder 0. Again I am going to divide 2. 2 does not go in 1. 0 times it will go. But the remainder will be 1. Now I have to read it from bottom to top. 101. So 101, that is number 5 in binary. Similarly, another example is 7. You divide by 2. 2 3s are 6. It will go with remainder 1. In 3, 2 1s are 2, remainder 1. Again, 2 will go 0 times in 1, remainder 1. Again, reading from bottom to top, the number is 111. That is our number 7. Similarly, you can do for 12. 2 6 are 12, remainder 0. 2 3s are 6, remainder 0. 2 1s are 2, remainder 1. 2 0 times in 1 with remainder 1. Again, read 1 1 0 0. That is what I am written here. Next, number 44. Divide by 2. What is it? Please try it yourself. 22, remainder 0. Again with 2 you divide, 11, remainder 0. Again with 2 you divide, 5 times it will go with the remainder 1, because 2 by the 10, 1 is the remainder. Then 2 2s are 4, remainder 1. 2 1 time it will go with remainder 0. Again 2, 0 times in 1 with remainder 1. So read it 1 0 1 1 0 0, 1 0 1 1 0 0. That is our number 44. So this is how you can convert decimal to binary. You can try your examples. Let us see how to represent integers using this representation. Let us consider the case of a microprocessor. 8085 is an Intel microprocessor with 8-bit register. That means there are 8 bits in which you can store the data as 0 or 1. So how to represent numbers in this 8-bit? That is what we are going to discuss now. This is the 8-bit where you can assign values 0 or 1. 0, 1, 2, 3, etc. You can see there are 8 bits. 0 to 7 is 8-bit. So in this 8-bit, these are called locations. memory locations where you can assign values 0 or 1. We are keeping this last digit, that is the 7th one, 8th one, 0, 1, 2, 3, etc. That is the 8th bit as the sign bit. We are keeping it aside. We are not giving it any particular value other than that attributed to sign. If it is a positive integer we are discussing, we will give this as sign 0. If it is a negative integer we are discussing, we will give it a sign. We will assign the value 1. 1 indicates a negative integer, 0 indicates a positive integer. Then you have to give the values in each of these to the corresponding number. For that, suppose you have to represent the number 5. The number 5 is 101 is the value of 5. It requires only 3 digits to express. But we have to represent that in an 8-bit arrangement, out of which the 8th one is the sign bit. So in the rest you have to assign these values. You can extend any number to any bit provided you add zeros to the whatever left. How many digits are there to be added, you can place 0. Just like the value, suppose you are having a decimal value, say 32. Its value will not change if you keep on adding zeros on the left side. Similarly, you keep on adding zeros on the left side, its value will not change. You can represent the very same number 5 in the 8-bit in this form. All the others you are keeping as 0. So like that we will be assigning the numbers in this registers. So this is an 8-bit register where you can represent the numbers. You have whatever number you have, you will be representing in an 8-bit format, out of which the first digit is for the sign to indicate whether it is a positive integer or negative integer. So up to how many, we cannot go infinitely to very large numbers using this 8-bit register alone. So you should know how much is the maximum capacity. What is the maximum number you can represent using this 8-bit processor? Okay, for that let us have a look at, suppose you have a word of length 2-bit. A 2-bit means 2 locations are there. Okay, so suppose these are the 2 locations. You can write out what are the possible values in this location. It can have value. First value it can have is 0, 0. The next value it can have is 0, 1. Next it can go to 1, 0. Then 1, 1. So in this 2-bit arrangement, the maximum value it can have is 1, 1 represents 3. It has got 2-bit. So 2 raised to n minus 1. Here n is 2-bit. So it is 2 raised to 2 minus 1. The value is 3. So 3 is the maximum value you can give in a 2-bit register. Like that you can, if you keep on adding the number of registers according to the value of n. This is n is equal to 1, 2. N is equal to 2. Like that if you go on, you can find out what is the maximum number possible. So for a 2-bit word, the maximum it can represent is 2 raised to n minus 1. But one thing you should understand, we are assigning, keeping apart 1 bit for the sign, whether it is positive or negative. So how much is available for us to indicate the number? 1 is going for the sign bit. So remaining we have only 1. So even if you have taken a 2-bit arrangement, 1 bit goes for the sign, the other bit only you can take for the numbers. Okay, value of the numbers. So this will be 2 raised to n minus 1. And in this case, in the 2-bit arrangement, the number of bits is 2, but only 1 bit you have to keep aside for sign. The remaining is 2 raised to n minus 1. Okay, so 2 raised to n minus 1 minus 1. Earlier both we could use, so the number was 2 raised to n minus 1. Now even if there are n allotted, 1 is kept aside for the sign, so the remaining available will be 2 raised to n minus 1. 2 raised to n minus 1 minus 1. This will be what remaining for us to give the maximum value of the number, because 1 of that always goes for the sign. Coming to 3-bit arrangement, again 1 part goes for the sign. What remains is a 2-bit, that is n minus 1. 3 is the n value here. So 3 minus 1 is 2. So this is 2 raised to 2 minus 1. That will be the maximum value you can give to a 3-bit word. Its value is 3. Like that you can go for any number. 4-bit means first again for the sign. The rest you can give the values. So again 2 raised to 4 minus 1 minus 1. Like that you can go up to n number of values. 2 raised to n minus 1 minus 1. So this is the maximum value of the digit you can assign to a particular word. Depending upon the word length, you are keeping aside one leftmost digit for the sign to indicate whether it is positive or negative. If it is a positive integer, it will be 0. If it is a negative integer, you will represent by 1. So this is how you represent numbers in a, this is an 8-bit processor. Usually it is Intel 8085. So like that you can keep on adding. If you want to go for larger numbers, you keep on adding the number of, you can increase the size from 8-bit to 16-bit, 32-bit and so on. So the word length, you can see the maximum value you can represent goes on increasing. That is how we store numbers in a processor.